So, we continue our discussion on higher order autonomous linear systems. In the previous lecture, we took a general nth order system and we said that an nth order system can be represented by a matrix equation which is given as d by dt of the dynamical vector, which is multiplied by the matrix A multiplied by the vector itself. And we said that there is a very close similarity to the first order dynamical equation, where you can simply substitute the first order variable x by the vector x and the variable A by the matrix A. To solve such equations, we said that the solution is given by x is equal to summation I goes from 1 to capital N C I e to the power lambda I t multiplied by V I, where lambda i's are the eigenvalues of the matrix and V i's are the corresponding eigenvectors. We said that we will take the case of second order systems because of their relevance, and therefore, we will dedicate this lecture specifically for understanding the behavior, the dynamical behavior of second order systems. So, let us look into typical second order systems. So, as I made a mention previously, I can write an autonomous second order system as representative system as d x 1 by d t is equal to A x 1 plus B x 2. I want the system to be coupled, and d x 2 by d t is equal to C x 1 plus D x 2. Okay. Now, the first step to do this analysis would be to convert this system of equations to a matrix equation. So, I would write this set of equations as a single matrix equation as d by dt of x 1 x 2 to be equal to A B C D multiplied by x 1 x 2. This is my dynamical equation. Let us remind ourselves that this is of the form d x under bar by dt is equal to A double under bar x single under bar. Okay. When I wanted to look into the dynamical behavior of the first order equation, which was d x by dt is equal to A x, I basically saw that there are two behaviors. One is exponentially growing behavior, and this was for A greater than 0, and the other was exponentially decaying behavior, and this was for A less than 0, right. And you would see that A in fact is an eigenvalue of the operator d by dt. Okay. A in the previous case is an eigenvalue of the operator d by dt, where you can say that x is the eigen function. So, similarly, in our current case, I can look into the eigenvalues of A and comment upon the behavior. In the previous case, the system had a bifurcation at A is equal to 0. So, the value of A, the sign of A determined the fate of the system. In case of second order systems, what I would need to do is, I would need to look into the eigenvalues, not simply A, but all the eigenvalues of the matrix A to determine the future of the system. So, let us focus on one of such cases. So, I have case 1 where my matrix is of the form A, it is of the form A 0 0 b. Suppose you have a dynamical system which can be modeled such that the matrix A is nothing but A 0 0 b. In such a case, I encourage you to determine yourself that lambda 1 is A and lambda 2 is B, and correspondingly V 1 is 1 0 transpose and V 2 is 0 1 transpose. Okay. So, now if this be the case, then what would be my solution? My solution would be x 1 x 2 is equal to C 1 e to the power a t 1 0 plus C 2 e to the power b t 0 1. Okay. This is my solution. The solution to the system of equations of the form which is given by equation 1 or the corresponding matrix equation 2 would be given by equation 3. Now, how would I determine the general behavior or nature of the solution which is given by equation 3? I will need to look into the magnitudes as well as the signs of the eigen values. So, let us consider case 1 a. Okay. So, I have, so my general solution is given by this x 1 x 2 is equal to C 1 e to the power a t 1 0 plus C 2 e to the power b t 0 1. Okay. Now, if I want to plot the variation of x 1 and x 2, then how would I do? Let us say that I plot x 1 versus x 2. At time t is equal to 0, at t is equal to 0 and for C 2 is equal to 0, right, for C 2 is equal to 0, because I will have all combinations of C 1 and C 2 and all of them would satisfy the solution. So, one of those would satisfy the condition where C 2 is equal to 0. So, at t is equal to 0 and C 2 is equal to 0, my solution is simply C 1 times 1 0. Right. And further I can set C 1 as 1, which would give me simply the solution as 1 0, right. So, therefore, 1 0 is a solution, 1 0 is a solution. But now I can set C 1 as 2, which will give me 2 0 as a solution, which means I have this 2 0 as a solution, and I can go on, and this will give me this entire line as the solution line. Okay. So, this entire axis is in fact a solution to my system of equations. Similarly, now I can do at t is equal to 0 and for C 1 is equal to 0, I can write x 1 x 2 as C 2 times 0 1, and following the exact same analysis, now I can draw this entire x 2 axis as the solution to my system of equations. Fine. Now, the question is, what is the nature of the curves which go along x 1 and x 2. Okay. So, now I have a case 1 a, where I say that a is less than 0 and b is greater than 0. Okay. So, here in this a is less than 0 and b this is greater than 0. So, therefore, e to the power a t will be equal to 0 as limit t tends to infinity. So, as time goes to infinity, e to the power a t would become 0. Therefore, this vector which is along this axis, which I am representing by this, will be the solution as I go to as time t tends to infinity. So, this is going to be a stable line, whereas limit t tends to infinity e to the power b t will tend to infinity, right, will tend to infinity. That means, what? My system is going to diverge along this curve, fine. And then what I see is that my system of equations is d by dt of x 1 x 2 is equal to a b c, in fact a 0 0 b multiplied by x 1 and x 2, and if I want to determine the equilibrium solution, then my equilibrium solution will simply be given as this is equal to 0, which satisfies x 1 equilibrium, x 2 equilibrium to be 0 and 0. It is not very difficult to solve this system of equation. So, my equilibrium solution for this system is this point 0 0, okay. And then what I see is that when along the x 1 axis, the system converges, and along the x 2 axis the system diverges, right. So, how do I draw the direction of the time? So, the problem in this particular diagram is that there is no time, there is only x 1 and x 2. Okay. So, let me draw the phase portrait elegantly. I have this x 1 axis which is stable. So, therefore, I can say that wherever I start from, I am always going to come towards this point 0 0 0, because e to the power a t for a less than 0 is going to converge to 0 0. And this is exactly the opposite case for the other axis. So, therefore, I would have the direction of the time being denoted like this, right. Now, this was the case when one case when C 2 was 0, in the other case C 1 was 0. Now, when I introduce both C 1 and C 2, what is going to happen is that I am going to go into one of these quadrants, either this or this or this or this, depending upon the values of C 1 and C 2 that I choose. Okay. So, therefore, when this happens, when C 1 and C 2 are non-zero, and depending upon whether they are positive or negative, I am going to get one or the other points in these 4 quadrants, and therefore, my solutions would look like this. I would be present in one or the other quadrants. So, these are the phase lines. Okay. So, if I start at any one point on this phase line which is going to be the solution. How am I going to evolve in time? So, I need to give the direction of the time on this plot, and that is not very difficult. What I see is that along the x1 axis the system is going to be convergent, and along the x2 axis the system is going to be divergent. So, therefore, the direction of time is this. For this quadrant, the direction of time would be this for this quadrant. Similarly, it would be this in this quadrant and this in this quadrant. The arrows, I must repeat, give you the direction of time, because the plot has been drawn for between x1 and x2. So, when you go along the direction of the arrows, you are basically evolving the system in time, and therefore, what it basically says is, what this phase portrait says is that if you start with any one point along the x1 axis, you are going to converge. So, therefore, the value of the variable x1 is going to go to 0, and the value of x2 is going to diverge to infinity. Now, imagine a case where instead of this, we wrote here a1 greater than 0 less than 0 and b greater than 0. I have the exact opposite case where a is greater than 0 and b is less than 0. What is going to happen in that case? In that case, what is going to happen is that this 2, so this is a greater than 0. So, this axis will become the unstable axis in the second case, and here b becomes less than 0. So, this axis now will become stable axis, and I then leave this as an exercise for you to determine the direction of the arrows. In fact, all the arrows will have exactly the opposite direction. And what kind of phase portrait is it called? This phase portrait is called saddle solution. Okay. So, why is it called saddle? Because from one direction you go towards minima, from the other direction you go to the maximum. Maxima means you go the system diverges to infinity. Okay. So, therefore, it has a saddle like behavior, and such solutions are called saddle solutions. Now, we take another case where you have our equation is this d by dt of x1 x2, this is equal to a 0 0 b multiplied by x1 x2. Okay. And now, you have a greater than 0 and b also greater than 0, and you can write a greater than b greater than 0. Okay. So, my solution is given by the same equation x1 x2 is equal to c1 e to the power by at 1 0 plus c2 e to the power bt 1 0. The equilibrium solutions remain the same. So, therefore, I will have the same point 0 0 as the equilibrium solution, and the axis would be x1 and x2. But now, what is going to happen is that a is greater than 0. So, limit t tends to infinity e to the power at would tend to infinity, and limit t tends to infinity e to the power bt would also tend to infinity. Remember, in the previous case, one of them tended to 0, the other one tended to infinity. That is why we call the solution as saddle solution. Now, when this happens, both the solutions, so we had these we had marked these solution axes, and now both the axes are unstable, and how do I draw the phase lines? This is the question. Okay. So, this infinity, the system goes to infinity, which means that the system is divergent, but how do I show this divergence? This is the question. For that, I need to do one thing. This particular system of equations is such that you can write the solutions of x 1 and x 2 in explicit form. Okay. So, if you solve for x 1 and x 2 using equation 1, what you will get is that x 1 is c 1 times e to the power a t and x 2 is c 2 times e to the power b t, right. I do not know the slopes of the curves which would be present in the 4 quadrants. This is the problem. So, then what I would do? I would play a trick. From here I would write d x 1 is equal to c 1 a e to the power a t and d x 2 is equal to c 2 b e to the power b t. From where I can write d x 2 by d x 1 is equal to c 2 b upon c 1 a multiplied by e to the power b minus a t, right. Now, I have some idea about the dependence of the slope on time. Okay. I have some idea about the dependence of the slope on time, right. So, as t tends to infinity, what happens to the slope? You see here you have b minus a, and in our case b is less than a, which means b minus a is negative, okay, which means that the slope as time t tends to infinity is going to diminish to 0. The slope should become 0. This is what I learned from this expression. Okay. So, how do I draw a set of curves such that as time t tends to infinity, the slope becomes 0 and at the same time there is no t anywhere here on the face portrait. So, let us see if the curve which I draw satisfies this condition. Okay. So, if these are two curves on the phase plane, then if I draw a line like this, the direction of arrows like this, then what is going to happen? The direction of the arrow gives me the direction of time and the slope is tending to 0 here as t tends to infinity. In this case, in this case, in this case, in this case, in every case. So, therefore, as time t tends to infinity, the system is the system diverging? Is the system going to infinity? Yes, the system is going to infinity, but is it also satisfying the condition that the slope must converge to 0? Yes, it also satisfies the condition that the slope must converge to 0. So, now I can draw certain other lines as well. These all are supposed to meet at 0, by the way. So, these would be the solution curves where they all emerge from 0 0 and then they go to infinity, satisfying the condition that the slope at as time t tends to infinity tends to 0. Okay. And if I follow these curves, do I get the correct nature of these unstable curves? Well, you see all the curves are pointing out. So, therefore, on this x 1 axis also I will point it out, on this y x 2 axis also I will point it out, again along positive x 1 axis I will point it out, and along negative x 2 axis I will point it out. And since I have written that x 1 and x 2 axis are unstable axis, in fact, I should have drawn the arrow outward. which is actually satisfied in this condition also. Okay. So, now since you start from 0 0 and you emerge out, these solutions are called source solutions. Okay. These solutions are called source solutions. So, we had case 1b where you get source solutions because you had the eigenvalues, both of which were positive. Now, you can do one trick. You can have a situation. So, let us quickly draw this. We had a greater than 0, we had b greater than 0, okay, and you drew these as the solutions, right, and all of them were pointing out. This is x 1, this is x 2, and the condition was that a is greater than b is greater than 0. Now, what is going to happen when a is greater than 0, b is greater than 0, but b is greater than a, in which case we will do the same analysis for the gradient, for the derivative, and then in this case I am pretty sure you would be able to figure out that you will get the phase portrait like this. You have pointing out, arrows pointing out, arrows pointing out, and now as time t tends to infinity, the slope should tend to infinity. Please do these calculations by hand, and if you find the derivative dx 2 by dx 1, e to the power b minus a term would appear, and since b minus a is positive, the slope should tend to infinity. So, how would I draw the curve which would show that the slope is going to infinity? Please convince yourself that these are how they would look like, and again this would be the direction of the time. Okay. So, this is also a source solution. Finally, we have the third case where both of the eigenvalues can be identified as negative. So, dx, so we have d by dt of x 1 x 2 a 0 0 b x 1 x 2, and now we have a less than 0 and b less than 0. What is going to happen? Well, you will have the solution as x 1 x 2 is equal to c 1 e to the power a t 1 0 plus c 2 e to the power b t 0 1. So, therefore, like the previous case, what you would find is that the axis x 1 and x 2 in fact are the solutions. These axes are the solutions. This point is the equilibrium solution, and now the question is what happens as limit t tends to infinity e to the power a t when a is less than 0, this is equal to 0, and similarly limit t tends to infinity e to the power b t when b is less than 0, this is also 0, which means that both the axes now x 1 and x 2 are stable axes, and if x 1 and x 2 both are stable axes, I can draw the arrows like this. They are all converging to 0 0. I will again ask the same question, that what would happen to the quadrants which are or to the regions which are away from the axis. You can repeat the exact same analysis of the solution being given as x 1 is equal to c 1 e to the power a t, x 2 is equal to c 2 e to the power b t, which means dx 2 by dt by dx 1 dx 2 by dx 1 will be equal to c 2 b by c 1 a multiplied by e to the power b minus a times t, and then for the case where b is greater than a, for the case where b is greater than a, the slope would tend to infinity. Dx 2 by dx 1 would tend to infinity. So, how would I draw such curves where the slopes tend to infinity? Now, in this case the direction of the arrow is inward, therefore, the direction of the time is inward. So, here in this region the slope should become infinity. This is very different from the previous case. At the center or at the origin, the slope should become infinity, and you see here that if I draw a curve like this, here the slope is infinity, right. This is exactly opposite of what we saw in the previous case. So, the direction of arrow would be this, and I can draw several of such curves. Okay. And then what would be the case when a is greater than b? Not very difficult to figure out. They would be directed like this, like this, these being the directions of the arrow, and so on. So, what is the nature of the solution? Such solutions are called sink solutions. Such solutions are called sink solutions. So, what we saw today is that you can cast a second order dynamical autonomous system in the form dx by dt is equal to a x, where x is the vector, dynamical vector x, a is the matrix. You can determine the eigenvalues and eigenvectors, and for the case where the where the vector is of the matrix is of the form a 0 0 b, only for such a case what you can do is you can determine the solutions as c 1 e to the power a t 1 0 plus c 2 e to the power b t 0 1. What is going to happen is, now the nature of your solutions will depend upon the values rather the signs of a and b. When one of the eigenvalues is positive and the other eigenvalue is negative, you get saddle solution, where one of the axis is going to be a stable axis, the other axis is going to be an unstable axis. When both of the eigenvalues are greater than 0, they are positive, the system is divergent, both the axis would be unstable axis, and you will get source solution. Similarly, you will get the exact opposite result when both the eigenvalues are negative, both the axis will become stable axis, and the solutions would be called the sink solutions. We will take a case of completely different form of the matrix A in the next lecture and see how this can affect the nature of the solutions. Thank you.